This one, right? Yeah. Okay. Good afternoon. Myself is Vybhav. Somewhat familiar, unfamiliar to this place. So I work at ARTPARK, where we do some work on climate and health related areas. And I collaborate with Professor Ravi and Professor Vijay Chandru. Both of them are here, along with many of Professor Ravi's MTech students. Okay. So I took courses here. I was taught by Jay Sukatme and Sen Gupta and others. So I did my work on cumulus parameterization, both using experiments and numerical simulation. So after my PhD, I said goodbye to turbulence and cumulus parameterization because of successful failures. And then I ended up, wandering here and there. And Professor Vijay said, "Come, let's do some work on not on fluid mechanics, but something else." I didn't know that the destiny was again they will put me back to this. So, and with Professor Ravi and him, now I started to slowly get back to heat and then now to Monsoon and eventually to cumulus parameterization. Anyhow, so ARTPARK situated in the IISc campus. It's next to management and between management and high voltage engineering. Okay, so I'll begin my talk this way. Please don't take it in a wrong sense that atmospheric science or meteorology is not. I mean, not only forecasting, there are other aspects. But what it gives you a message is, I think there was a issue which I think Professor Ravi has shared it with me. There's a collection of articles, one of the popular journal accumulated, and many weather experts, forecasting expert wrote that it will take another decade to build a complete AI-based forecast system. Just 3 to 6 months down the line, the Caltech group and NVIDIA produced this. Okay, so this is how sometimes the technology changes. And this is what my mentor, Professor Odam, always used to tell, that whatever experts sometimes predict, things will go in, completely in the other direction. So, but again, it's not that whole story that everything can be replaced, but this is one part that, it is making a large progress. And the spirit for this comes from computational positivism, which, Professor Odam advocated. It's a very nice, interesting article. I think it's available online from EPW. It's very neatly written. And it basically comes from the two cultures of doing science, axiomatic as well as, based on observation. So he used to call as, Babylonian or Indic versus Greek way of doing science. And Professor Vijay Chandru kind of popularized it and also adopted for the work in biology. And it was Professor Narasimha's dream that we should do more, involve more in doing machine learning and deep learning work related to that. And he told me just before he passing away, I was finishing my thesis, that Vybhav, you come back and we will work on monsoon modeling using deep learning or machine learning. Okay, this was just pre-ChatGPT era, so he was very optimistic, but he also knew the limitations of this. Okay, he never wrote it down, but he has told many stories about it. Okay. Since I worked on numerical simulation, deep learning, I think now everybody knows this is just an introduction part. How to? Okay. So it's just that, you feed data and system will learn the rules. It's not like you are giving the rules and getting the thing, which I think you are all familiar with that. And the deep learning becomes extremely popular because the more and more data you feed, unlike the classical machine learning model where they saturate, it doesn't matter how much of data you feed, they will just, unless you come up with a new way to do a feature selection. Deep learning is not like once you have a large amount of data, the large neural network the performance keeps increasing. Okay, so this is the advantage we have. And it's a brute force method of doing things. Okay, same like direct numerical simulations. Like once you have equations set, you use finite difference or finite volume and use all possible clusters and run your simulations and get the result. But the big difference comes is how the truth is. One comes from the physics equation. while the other comes from the data. Okay, so you want for that, but both are driven with high amount of computations. Okay, so I have three problems to talk, but this is something I worked actively. So I'll talk a little bit more on this, although this is not a season for heat stress, but I'll just talk about it. And so there was an article which was sent to me by Professor Vijay Chandra on India is underestimating the number of people dying due to heat waves. So we started looking into heat waves, I think in 2023. While doing that, there is one very nice piece written by Professor JS in Current Science. I think it's a guest editorial or somewhere. It's called The Existential Threat Posed by Humid Heat Waves Due to Global Warming. So this was my first reading on this particular work, and it's very well written. And here, this is not from this paper, this is from some other thing. So what we are showing, this plot shows is, if the number of heat wave days increases, let's say going from 6 to 8, what is the consequences? You see the rise in the mortality. Of course, there is some amount of theoretical calculation has gone into this, but this is what they estimate. This is for Indian region, by the way. And similarly, if you go by 0.5 degree increase, and what happens to the mortality rate? So it was us to do some thinking about it. This is not a small number, okay? And they have been estimated with all possible error limits. So even if you take it goes by 46 to even 65, that itself is quite large. And India being vulnerable and high population, so we thought we'll look into this problem. Okay. So, but how do we look into this problem? Like, we need some stakeholders to take our results. It's not only for pure research, it's an translation research. So we looked into what IMD is doing. Okay. And what they do is some district level based, yellow, green, alert. Okay. And they would use only the temperature based criteria. It's been followed throughout and they are using that. Okay. But that's not the story. We need more variable than the temperature. As I told you, that humid requires humidity into the picture. So what we wanted was not just only the district level, you want at a slightly hyper localized at a sub-district level, or even at something like 10 kilometer by 10 kilometer, so that you could take more action. So what it means is that, for example, entire district is it heat prone? It may not be. Many times that doesn't work that way. So only the part of taluk will be hit by the heat wave. So it becomes government to take the necessary mitigation strategies. And what we wanted to use was, instead of just temperature, we wanted to use humidity, wind, and radiation. Also include some component of health and vulnerability data. Okay, and we wanted to do this as a targeted risk communication. And this is some sort of a chart that we have now, and we have built it and it's deployed. It's a work in progress. Okay. This is the grand plan, and here we are collecting the data from the climate end and some from the health data that is completely lacking, to come up with a threshold at what rate we should start to give an alarm. Now, this heat index or heat risk index, it is based on the US metric, but we want to identify and validate whether this same thresholds will work for Indian context or not. Okay, and for this we need some health data. We looked into the government portals, and we have active collaboration with Karnataka State Health Department. And there is not much data has been collected on the heat-related illnesses. So we started to do a primary research on data collection itself. Okay, that is in collaboration with MS Swaminathan Foundation and IISc Center for Public Health. So the overall goal is to have a personalized data and combine that with your meteorology and come up with the targeted heat index risk dashboard. Okay, our personalized app. So forget about this part for a time being. Now we focus on this. Now so to come up with forecasting, I need some data. Okay, so when we looked into IISc, they just only give you the warnings or some numbers. That is not sufficient. So, and we can't run the conventional forecast models on the computers that we have now. So to rescue that, AI came into the picture, which I could now every day 5 models run in IISc, your CAOS cluster. We have all the data. I'll talk about that a little bit later. And these are the different models that have been AI-based models. Full end-to-end. You take ERA data, feed to the model like a previous one time step. Okay, like how you initiate your the conventional forecast model. take that and feed it to the numerical model, and it will give you the results in about 5 to 10 minutes, depending upon the model. Okay. For 15-day forecast, I take about 10 minutes, including data writing onto my computer. Okay. So these are the different versions that we run. And this IFS is from European agency, ECMF. This is for comparison. And these are for different architecture. And these are the output lead time, how they provide. And they will give both surface as well as pressure level variables. There are about, I think, 77 plus variables. Okay. So, yeah, sure.
Clarification. So, the ERA integrating data, ERA 5 analysis you are using.
Yeah.
So that has a backlog.
Okay. So now what they are doing is the initial model that they run for IFS forecast, that they are giving it to us. You have that initial data for that.
So you are up to the previous day.
Just up to the previous day. So every day 2:30 it gets updated. So every 6 hours, UTC 00, 06, 12 and 18, it gets updated. So yeah, I have that data also, like if anybody wants to run. Okay. But before that, we wanted to test, whether this can be leveraged for our work or not. Okay. This is very high level overview, and we are only doing it for Indian region. Okay. We have forgotten about ocean and others. Only the land part of India we did. And also there have been a lot of claims saying that, AI is going to replace the conventional forecasting and things like that. I don't know that will happen or not. And you can debatable on that. But what we wanted to check was, at least is AI-based forecast is on par or at least better or slightly worse, whichever way, than the conventional system. The two color are one from deterministic forecast, and this is from ensemble forecast. Okay. And the gray ones are three different models. You could do for others also. But these are the three models. One is Pangu from China, and same Fuxi, and this is from Google. And you could see that the Fuxi model almost close to what you get from ENS mean. Okay. And so we run on this forecast, and we have the model in place.
So that gray line, so that what you want to see the top 3 lines.
Yeah.
Are from the statistical models.
These two colors are from the conventional forecasting, from ECMF. Okay. And the gray ones are from the AI-based.
Okay, the corresponding here.
Corresponding. Okay. So they both exhibit very similar.
Yeah,
error.
similar.
Yeah. Okay. So if this has been used for operational forecast, I can use for our operational forecast. What I'm saying is, even this IFS, HRS, and ENS, the simulation data is also out for public. Anybody can run it and utilize it. Now, downloading the data will take me about 2 hours. That's a problem. It's a huge data set. So, and then we wanted to look the scorecard, and so we kept this as our base model. Don't worry about the numbers here. This is just the RMSE that you saw here, and this is compared against ERA data. The ground truth we have taken is ERA and compared it, and this is the RMS. Okay. Now, if the model is good, performs better than this is now 0. I mean, the color, some kind of gray or white reference, that's a 0, that's a standard. If it's on towards red, the model performs bad in comparison with the deterministic model. And if it's blue shade, it does better. Okay. So we checked these parameters. The Pangu weather slightly on this side, okay, meaning slightly worse than this, which was also evident in the plot. And the GraphCast and Fuxi were doing as good as or better than this model. Okay. This is just to showcase. And so what we did was, before building the multi-model ensemble, which Karan has put his effort for his thesis, we initially just took, okay, for day 1, I pick data from GraphCast, for day 3 GraphCast, and for 5 to 10 days, take from Fuxi. Okay, this is what we have done. Okay, and then these models will have bias. And when one of your MTech student Rahul did some initial work, and so there is some cold bias in the model, especially on the GraphCast, and we wanted to remove the bias also. So we removed the bias using both the mean bias as well as mental mapping. Is essential to look for extreme events, and we made sure that there's no bias, or there is very little bias in the system. And this is for all India. And this is a temperature forecast just to show that you could do it for any regions and for 10-day lead. Okay. And now what we have is a small, it's for our internal purpose. I have not yet made it to public. This is a small dashboard where these are all the models. I can select whichever the model I want, and I can look what temperature they have, look for the forecast day and forecast hours. And I also can click for comparison for all 6 models. It will compare. And also it will look for model validation on a daily basis and all the model details. I've put this forward. I'm just looking for one good front-end developer who could, make it more efficient and, put it for public. And I want to make all these things public for all the CAOS and everybody. And I'm happy to give all the data sets, which is already been stored in the CAOS, by the way, now. Okay, so now we got this thing. So we have now the parameters, and we would like to now do some analysis on that. And so our first analysis is the maximum temperature, and this is the criteria that IMD suggests. Okay, and apart from that, we validated with 2-3 other parameters that is used in operational forecasting. Okay, so excess heat factor is used by Australia, which considers average temperature rather than the maximum temperature, and it also looks for the long climatological average, and which is called significant factor, and acclimatization. For last 30 days, how was your weather? For last 30 years, how was your weather? So it takes 2 parameters. We can discuss this further. I'll just stop it here. And then there's another one which feels like temperature, which takes humidity and temperature, which is, when a person is under the shade, what is the heat he experiences or he or she experiences. That's a feel like. And there's a criteria that they have put. This is again by NWS. Okay, it's developed by Stedman in 1971, and till today we are using it. It still has to undergo some more processes. And for Indian context, there have been severe questions on the validity of this model. And till the health data comes, we still don't know. The other one is wet bulb globe temperature, which is being used in an operation in outdoor setting. Okay, mostly for occupational and sports, and which takes into consideration the wet bulb temperature, the globe temperature, and the air dry temperature. It takes into that. So we wanted to assess all these 4 and see whether do they really make any difference, or can I just go ahead with whatever IMD gives? Okay, because this is more easy to interpret than this and this. It's not that easy to communicate. We have to communicate this with the health officials and government officials. They are very familiar with this terminology, but we are not with this. So we wanted to check whether can we just use this and get away with that. And I'm just showing, I've taken 2 parts of Karnataka. I'll just show the Karnataka's map. And yeah, so I've taken one here, near where the heat waves are severely prone. The north interior region, we call it as. And the other one is the coastal Karnataka, okay, where the humidity matters. So these 2 locations I've chosen just for an example purpose. Okay, so I've taken the green represents the 2024 in I think all the plots, and the blue represents 2023. This is the max, and the dotted one is the average temperature. Okay, so if it crosses beyond the 40 degree that criteria for 2 consecutive days, then it is called a heat wave, and if it doesn't, then it's not a heat wave. That's the criteria, and this is what it shows for the North Interior, and during 2023, there were not many heat waves, and 2024 had some heat waves. The next one is the excess heat factor. This excess heat factor will tell you if this number goes beyond 0 or goes 0, greater than 0, then that's a heat wave day, which is very easy to interpret. And if it's below 0, then there's no heat wave days. Okay. The other one is the heat index, feels like temperature. Anything that you are seeing in red, that's danger. Okay. And the orange is just, like an alert. So you could see that in 2024, for about almost close to 10 days, you're having very high heat stress scenario where the high max temperature may not capture the entire scenario. According to IMD, this is not in heat waves from 16 to 28. Okay. They declared for me here, but it was not. So similarly, we plotted for 2023, there were not many heat wave days. Then we looked into the wet bulb globe temperature. Here, if it crosses beyond 27, that is risky for workers. So we didn't cross beyond that. Also, we need to validate the way we have calculated in the sense that I'm using ERA data for that. I have not done the correction factor for this. So I need to do that, but this just gives you the picture. For that purpose, I'm showing. Now, this is for the coastal region. There, the temperature may not go up very high. And similarly, the excess heat factor also, you could see that it is positive, meaning this is a high heat event and there are two places heat event. Although the temperatures are at 35, the excess heat factor does capture some aspects of heat wave. Now we look into the features. Very high, but it's still high. But you now look at the wet bulb globe temperature, gives a different story on that. This was more prone to, both years are more prone to heat wave kind of scenarios. So we need to check this, but by and large, I've made sure that these are all validated. But this globe temperature, I have to identify whether I've considered all the parameters. I've taken incoming and outgoing radiation flux, but just as a word of caution, I'm just telling you. Okay.
What about this in ERA or ERA forecast, similar than how it, this is your forecast, isn't it?
This is both the forecast as well as, we have validated it. There will be an error. That's why I've taken it for 1 day. Just showed for with each day of that. What I'm saying is the forecast is taken for day 1 from the model. Okay. So for example, forecast for 2 was taken, forecast for 3 was taken like that day. So just to see whether it will calculate, because we know that in the forecast, if you do that, there is always an error, which is here, which will go. So I don't want that to disturb my calculations. So this is, I just wanted to validate this thing. So we have considered that. So with this, what we did was we gave out everyday heat risk at a taluk level to Karnataka State Health Department and the State Disaster Management and Regional IMD and also to IITM Pune, who are our collaborators. And we are grateful to IMD and IITM. They are being actively involved in this work and they're assessing how the models are doing and they're open for any discussion and suggestion. And they also provide me all the raw data. So this is the picture, and during this May this year we didn't have much heat stress days. So this is the way it gives. So every day we send it, and wherever there is an alarm for 3 consecutive days, we report the public health authority to take actions or develop mitigation strategies for that. Yeah. So this is what we did, and this is the operational mode. So every day we send this report to them. Okay. So I'll go to the next part of the problem, which is deep learning for downscaling. So now till now what we did was we leveraged the existing models and we just took the parameter and we deployed it. Okay. But what we want is we want to go even more hyper local. Can we go something like 5 kilometers or around that range? And we need to look for downscaling techniques. Okay. So there's one nice paper. I think this is, I think Ravi's one MTech student, Ananya. She did a part of the work here. And a very nice technique. When we read, at least on a theory on paper, it looked very nice. And I think they also applied it on a real-time scenarios. So this is a downscaling technique where they go up to, I think, 1.5 kilometers. Okay. And so we said, now to go to 1.5 kilometer or anything, we need station data. Okay. And IMD doesn't have these many stations. This is from all the dots. What you see here is from Karnataka State Disaster Management. Okay. This is the grid. What you see is 0.25 and this is 0.1. And so they have data from 2015 to recent, and we have regular daily access for the data. And they have about 900 stations, but I think the 500 odd are working fine. The remaining have not functioned on a daily basis. So what we wanted to do was to start with, we take 0.25 degree simulation and downscale it to 0.1 degree. That's roughly 11 kilometers. Now I think India gives you at around 1.2 degree, 1.12 degree. So we wanted to check, we downscale and check how the model performs. Okay. The technique that we have used is called unit architecture. So again, I'm happy to take any tutorial on deep learning related things. And if anybody wants to see how this has been implemented on ground, on reality, I can take a tutorial section and explain how well it works. So basically, the idea is I have a forecast and I decompose the forecast into a temporal dynamics and I will identify the spatial fluctuations. Okay. And now don't worry about it. This is a very complicated technique, or I don't know how to explain in simple terms. Okay, let me accept fault on my friend. So this is the architecture, and some of this, let's say, this is the I asked ChatGPT to explain to me, and so that I can show it. This is what it gave. So basically, it's a small input data, and this is 4x4, and then it's not 8x8. It's got graph. It's only 5x5. So that's how something is a mistake. So there is an encoder and a decoder. So the encoder compresses all the information, and in the decoder it gets expanded. And here in the unit connection, it will learn from two things: one from the ground data and also from the encoder. So it remembers where the edges are, where the values are, where the peaks are, and things like that, and to give the high resolution. Okay, this is all I can explain, but it's very easy to show on a computer how well it works using code. So if you people want to know, I'm happy to take one tutorial on that. Okay, on all these models, whichever I'm showing it to you. Okay, so this is the CAOS and DMC data, and this is what we have plotted here is the height, elevation, and these are all the rain gauges. This is from one of the AFS forecasts. These are the parameters, and these are the levels we get from CAOS and DMC hourly data. And this is how the raw data looks, the hourly data from one particular station, which let's say we are interested towards this part of the Karnataka where we know there are heat waves. So we have picked one of such stations and we did, I think Ananya did this work and cleaning the data set. And so we have done the gridding part of this data. So this is the different gridding techniques we have used. And we found out that the angular distance weighing, which is being used by Rajivan and others for IMD, it turns out to be the reasonably good one to generate a grid. Okay. So why we have to generate a grid? Because for me to compare the model, I need high resolution. Okay. To train the model. Okay. Once I've been trained, then I don't need it. Okay. So for that, I need the high resolution data. And then, so what we did was here, I'll just go back. So here, what we try to do is, this is the long-term mean. Okay. So for Karnataka, I calculate what is the mean temperature. Okay. That's all this term is. Okay. So this will remove any bias in the simulation. The mean bias that we did long back, just in the previous slides. Now this way it learns the features from inputting other kinds of data set. So here if we, for example, the elevation and temperature and humidity and rainfall, all this data set will be fed to this, okay, to this unit. These are all the data that we have provided. Okay, we provided land surface temperature, and other data set that is being given by the AFS forecast. And then we train the model. For ground truth, we have used that 0.1 degree gridding that we have leveraged. So with that, we got this. Now, so usually I know I also did the same way. Whenever our MTech thesis submission has to happen, that previous 2-3 days we'll slog and we'll work. And so this is what the results we got, but we need to, do a thorough validation. One set of validation has happened, and but we need to tweak the model to perform better. Right now, this is the downscaled data, and this is the ground truth. Okay, now this is at 0.1 degree, and this is at 0.1 degree. Both are at 1 degree. So that small here, it's not able to capture the high temperature which is there, which is not good. So we need the model to capture this. And similarly for the minimum temperature data. And here we compare that with AIFS forecast and with ground, which is now 0.5 degree. We are not converted to 0.1 degree. So just the raw data set. So we have the working code. We just have to tweak it a bit. And it's deep learning is like a parameter tweaking that we do for other work like cumulus parameterization. Okay. And now we calculated the lead time and then the model. So just focus on the green line and the gray line. So there is one small key that is coming here. We really don't know why that is happening. It is coming in the raw simulation also. And my colleague Karan also pointed out that for some simulation for him, there is a large error in the first day and then it goes down. So we need to check that why this, some model like GraphCast and AIFS does that, but the other model doesn't do it. So I particularly wanted to show, we want to understand why this kink, there's increases and there's a sudden dip and now it is captured by the unit also. Okay, so either you need to teach not to do this, or we have to figure out why this is happening. So there's small key, and you can see that when you do the model, the RMSE is up with the lead time has almost, if I take the average, it's close to 1.8 or let's say even 2, but which is going here. So this is for max temperature and mean temperature, and this is average metric over. So the AFS forecast at 1 degree. When I say you take a 0.25 and just do a bilinear interpolation, and you do that, you get this as RMSE. And for unit, I get about 1.8 degree, which is just telling that, okay, there is some merit of doing this work. Okay. I mean, maybe, hopefully, if you fine tune it, maybe we may get better results. Okay. But anyhow, our agenda is to give thresholds. So if we are working within certain threshold values, we are fine. Okay. And my last thing is deep learning for monsoon prediction. This is the work I recently started. So I don't have much authority, or I don't have much understanding of this problem. Okay, so I'm just doing whatever Professor Ravi suggests me to do. Okay, so this is a work which we are doing with one IISc undergraduate from math and computing. His name is Aditya. He's actively looking into this. And I think recently somebody gave during the Monsoon Cafe about this particular architecture. So this is the auto encoder, the same encoder, unit encoder you have learned. I mean, we just showed. There, what happens is the encoder learns to take a low resolution data and pumps in high resolution data. Here, what it does is it doesn't do that way. This is also an encoder decoder architecture, but it doesn't change the resolution. But it's a rather an unsupervised learning. It's like a principal component analysis analogy, where it learns the nonlinear patterns in the data. Okay, so we don't say, and it will only be given. So here, all the parameters that compressed learning will happen. So basically, if I have a 320 or 340 features, in the end, I'll get about 18 to 19 features. So that's all being learned. And we leverage that to make a prediction. So this is what we do. And these are the data set that we have used, geopotential height, zonal field, and sea level pressure. And we have used data from 1948 to 2024. This is at this grid, and when we fill it, we go from 10 degree to 20 degree. Okay, so you can already see that I myself doing some amount of feature engineering here, which is not good because I may be missing out on things. So we are now going from auto encoder to CNN based learning. But before we do that, we thought let's reproduce the results. We got a matching accuracy with the previous results. And so for this year, we just predicted. So I think I will give over next 1 or 2 weeks, I'll give for even homogeneous region. So we did it for testing. These are here. See here, don't take, this is the long-term average, that 1917 to 2020 rainfall. And this is this year prediction from these variables. So which we look like for all India now I'm talking about. This is for June, July, August, September. We are maybe just normal or slightly like below normal. But whereas IMD said that we are slightly above normal. So yeah. So yeah, with this, I'll end my presentation and I'm happy to take questions. Yeah, not on monsoons, other things. Yeah.
Interesting. We also got a very similar, forecasting for 2025 using AIML.
Okay.
My lab, whatever it be.
Okay.
Very, very similar.
Okay.
It doesn't come above normal the way IMD predicted.
Okay. Good. Thanks for validating. I was really worried when I wanted to present because I recently shared a few things with Professor JS1 data on that, where what the forecast gives versus what the reality was completely different. So I was just looking into it. Now we will do it for homogeneous regions, but we will now change the architecture. We go to CNN based. But yeah, this is what we got.
But my suggestion is like for when you are trying to forecast into it.
Yeah. So
you do the matrices for extreme temperatures only.
Huh.
Won't take all the conditions.
Yeah, very good point. So we are doing, I was supposed to give one more talk on that, where Professor J has sent one paper to Professor Ravi on extending the predictability limit. That is, they only consider the extreme temperatures and they train model on that. I thought if I start taking that, that will take half an hour session on that. So if required, maybe next sometime I can do that part also. Yeah, I will, that we will consider only the extreme temperatures. Yeah. Yeah, but we have to give for the entire Karnataka. This is for operational forecast purpose. So we have to do for the entire country. But I do take your point that, yeah.
But the problem is the sample size for extremes are always very small. So
Yeah.
really look for the right method to.
That's always unbalanced data set. And yeah, so we will have
Especially
to.
if you're looking at heat waves, then maybe what maximum of 10.
Yeah.
Yeah.
Yeah. The other thing is to do some GCM kind of simulation for 100 years and see you can train on that. I mean, those are all.
People have tried it out.
Yeah. How good? Yeah. Yes.
But your model need to always forecast less than observed. So why is that? Because like 2024, it did not come in correctly. Like all that I think is either less or at most equal.
I have no idea, to be very honest. Yeah.
So you're biased in the model. So
There could be a bias.
yeah, there could be a bias. You can be,
Yeah.
She had used for a different period.
Yeah. I mean, there are many techniques you could do it to overcome that. I just use the simplest thing.
You can't use only a regression or
Non-linear regression. Yeah.
there also, I think she took a combination of parameters
Yeah.
and also
Yeah.
techniques and then
Yeah. I think she went one step ahead than what we are. I think we will stop it here and move to CNN-based methods. Yeah. Because then I don't have to worry about myself manually aggregating 10 kilometer, 20 degree, 10 degree. So the CNN will take care. Yeah. And with this, I want to say that in ARTPARK, what we are trying to do is we are curating the weather data set from various agencies. I mean, I know you people will download and use it. So we are curating it and annotating it and attributing it to properly. And also we use averages, mean, whatever it requires. And so it will be out for you people to use it. And if you have any doubts or if you want any variables to be stored, it will be updated every day. I'm happy to discuss so that you don't have to go and say, for example, download from ERA every time. So it will be there. I mean, I can keep the system at ARTPARK, I'm sorry, at CAOS, and it will be like a user interface, like how you have ERA, and you could download the data set. Yeah. And any other open source data set you people have, observation data set, please give it to me. We will use it and I mean, we'll leverage it for all other people to use it. Yeah. Yeah. Given Karnataka experiences comparatively might have limited experiences, local historical affairs. So how do you address the challenge training, validating your model for forecasting, especially for rare or extreme event? Would be better to get some other state data as well. Yeah, we have tried it for Rajasthan also. I've not showed it because Karnataka, we had somebody vouch for that. We will use your models and forecast. We were giving it to Karnataka, but the model has been looked into Rajasthan and all India. That's why I showed you that there is an all India map. So yeah. Tamil Nadu, yeah.
and also I think MP has kind of
MP has want to, yeah, but so yeah, we need somebody who will every day vouch for the work and they will give feedback.
and the kind of density of
Station, yeah.
stations I think is highest in Karnataka as compared to other states. For whatever it's worth, it's still one of the best data sets that we can get from.
Yeah, no, I kept Professor JS mentioned to me. Sometimes you have to be very careful with Karnataka data set. So we have done all the. So that's why we are reiterating and doing all the calculation by ourselves.
I mean, it was a big start.
Yeah, it is it's a huge nice here. Yeah,
Time she spent to get it up for the hardware.
yes.
So on the use of the seed prediction.
Yeah.
For urban time,
Yeah.
what is the revenue need to get it down? Because, as we know, Kenya and
Yeah.
IISc campus,
Yeah.
there is a huge gradient and no, in some sense,
Yeah.
in the urban situation, for example, people are doing the street cleaning and the corporation employees, the stress levels, their back and forth or navigating over
Yeah.
in the cities.
Yeah.
How do you, what is the resolution that is needed?
Yes,
Hundreds of meters.
Yeah.
Hundreds of meters. And
So,
we have to go hyper. If you get real-time data, then maybe more like a nowcast. Right.
Yeah.
Or let's say 3 hours or 6 hours. And you could actually put sensors. Yeah. That is already available for the city.
There is a crowdsourcing we
Right.
are extracting from. Again, the validity of those sensors, how well they have been maintained, what are so those kind of things will come. But urban heat island is something. I mean, I personally have not explored this one. So that is something we will have to do it.
Lines over all these. Right.
Yeah. So because I don't have a necessary background in the GIS data analysis. So yeah, with that maybe yeah, yes.
Sorry, I keep on asking.
Please,
In your model, that this AI, that
Yeah.
this is Asian, there's a global, right?
Yeah, it's global.
How do they talk to the region in space? How do they talk to region?
No, it is so these are all like a vision transformer models. And also they are also known as a graph. Oh, sorry. I think yeah. There is also graph neural network model. So where you can go with the they call it as a depth search and breadth search. So you could go with, let's say this is my station one. You can go as much as information which is connected to maybe few hundreds of kilometers using the depth based search. So, or if you are in the CNN, it will learn the pattern of by by dividing the image into or earth into these many things, and so they learn the patterns, both the large patterns as well as the small. So one thing that I would like to verify is the spectra of forecast. So what I have seen is when I calculated the spectra with the lens scale. Roughly I'm showing, like for example, for all the AI model, it just works like this. But if I take AIFS, it will go something like this. So this dropping or smoothing of the data is something we have to understand. But I think that's they say it's an inherent to the AI model. So that is why whenever next time when I give you plots of this, that you can see that AI model doesn't have that the small fluctuation thing. They are more like average values. They look like more average. So
Because the input itself is smoothed at 25 kilometers.
I plotted the spectra for ERA. That also goes quite good. But when the model learns, and so this is where we don't know how long this spatial thing extends, and maybe with better resolution model, like you get 12 kilometers by 12. Yes. Yeah.
So in one of your plots,
Yeah.
in which you sort the RFC is going up.
Yeah.
In this there is a theme,
Mm.
there is drop of
Yeah.
constant, then
Yeah.
You said that right, you don't know why the drop is occurring.
Yeah.
Then you mentioned that we can like train the model to not do that. So do you have a plan how would you do that? Because these are frozen models, right? And we have got
It is coming for two particular models which were based on the graph neural network approach. It is not coming for the one which is made up of vision transformer based. Yeah, so I don't know why it is happening, and I think current probably you might have written to somebody, like why it happens. I remember you were saying, yeah. See, for example, current faced an issue. His initial error is very high, which is usually it is something like this. Your RMSE with this is RMSE and this is lead time. His was very high in the first day itself, so he was getting for some of his forecasts.
But that's usual for models.
What is fixed? It holds the model.
Yeah.
it was just with the initial recognition. There was some issue with the initial recognition of the code, so
Okay.
that's a for one of the models.
Okay.
But this is something different, I guess, because now it's getting higher and then dropping.
Yeah.
Yeah.
Yeah, no, I really don't know why it happened, but it happens for only GraphCast and the AI vectors which are based on graph neural network.
What are like in some sense classes?
They're very similar in approach. And this is some model which I think at CAOS, if somebody is interested, we should explore this model, the Fourier neural operator. It has also backed with nice mathematical theory. So unlike these things, but again, training that requires huge computing. So yeah, but to understand some physical phenomena and and it's very fast. It's much faster than any of these. Yeah. Okay, I'm done here.
Yeah, so in the last 1 week, it was a very interesting phenomenon. On Monday, essentially an IISc then was sitting just north of Hyderabad, okay? And today it has gone somewhere here, today at 11 a.m. So this keeps moving and it's a very steady movement and it will be in the close to Delhi by tomorrow, day after. And all of you know that in between it went through Mumbai. And Mumbai has a very nice urban radar network, which we don't have. You can see the gradient of rainfall. This is unbelievable. This is, of course, the 500 average is not daily mean. This is of the order of 50 millimeters in 5 minutes. Remember that. In fact, 50 minutes, 5 minutes. And right next to it is zero. So this is the challenge in rainfall forecasting on a short time scale. Very sharp gradients, which we never saw before, because we never had data. Okay? For the first time in India, we have a city with 100 rain gauges and 4 radars. So we're going to see a lot of interesting phenomena. So I encourage all of you, whenever there's rain in Mumbai, go look up that Mesonet. This one, very interesting data. I hope that all of everybody. You see there are 3 regions where very important is there. In between there's nothing. And you can see moving again, show the every 5 minutes. That's a nice change in time. Okay. Okay, let's come back to the all India level. So we are still below normal in August. Okay, although cumulative we are just above normal. And the key point is this country India in August was 35% below normal. Okay, this is August 19th. And so in the next 10 days, the system is going to move into central India. It's already there. It's going to move up. So the potential business will come down to not to zero, but very close to zero in another 15 days if possible. So we'll watch it in the next few weeks how this evolves. And you can see the core monsoon zone, we had this huge period from August 1st to August 15th. And it's all below normal. Now it is switched to above normal. It's not well above normal. So if this persists till another 10 days, August may not be a month with drought. Okay. And the other thing is, in addition to this all India picture, it's very important to know this structure. And that's put out by IMD very interestingly. So they only have 2 categories. Okay? One is normal and above normal. One is below normal. Okay. Now, this may seem strange to you, but this is convenient. In India, except for floods, which occur now and then in cities and so on, we don't care. Rainfall above normal or normal is okay for agriculture. Okay. So this is all classified as one category and this is one category. And you can see that in the last 13 years, only 2 years, we're close to 50% deficit. That is those 2 years. Okay. And after that, we have been very lucky. This is hovering around 20% of the district, with the district level, not division level. So this is a fine structure data. and it's showing that in a normal monsoon year, this is what is the number is affected by below rain. Most of them are very normal or below normal, okay, till today. And that's reflected in this cumulative picture. There are only 3 subdivisions, all in the northeast and Bihar, which are below normal, okay. So I want to look at how good a forecast at the weekly level. Okay? We've been discussing that. So I looked at the observed forecast last week. This week is not available now. Is minus 25%. Okay. Now look at this prediction. 16 July for minus 11. 2 weeks back they were absolutely right, and then they went wrong. Okay, this is very surprising. As you come closer, you would think with all the simulation and all the power of satellite, that is good. So this is a very, it not doesn't happen always, I'm sure somewhere in the next few weeks. This is very surprising that 2 weeks back when right forecast and the forecast predicted normal last week, that is week before this, and actual value is 25. So to me, this implies some problem data simulation. So we look at it every week now. Let us see whether this problem continues or this is a particular problem. But I also looked at, say, IMD does a very thorough job called verification, but they don't do it in real time. They take their own time. Okay. So last year's monsoon is very well documented. All of you can download it. I just saw one figure to look at the weekly forecast. Okay. So this is the actual observation weekly around all India. And this is the forecast 1 week ahead, 2 week ahead, 3, 4 week ahead. Okay. So you can say here that 1 week ahead is very good, then it got very bad. But in the second week, second week is good, 1 week ahead, but second week it goes down. But most interesting is the last week of September last year, it had torrential rain, unbelievably large, and 1 week ahead forecast was totally wrong, too much. 2 weeks, the third week was right. Okay, that is surprising. So 3 weeks ahead, exactly like what happened here. 3 weeks ahead, they correctly got the weekly rainfall anomaly, but 1 week ahead, they got totally wrong. So it is worth, for those who are doing modeling, it's worth asking, what kind of error is there in the model which makes the first week so bad, and then it 3 weeks ahead is better. There's something there to learn in physics, but it's not clear what it is. Okay? And the same issue with extreme rainfall, which is a very important issue today all over India, because it causes so much damage. And you can see that various ways of looking at it, toss around ratio for extreme rainfall is as high as 30%. Okay? This is one of the problems we are going to face. If you keep saying every day there's extreme rain, people won't believe you. Okay? So you have to keep that not as far as possible. This is also very low. Directional probability. This is different models. Okay. So I'm surprised by, of course, multi-model mean always comes well as Vybhav or shown. It is operational, I don't know what that means. But all the other models are poor. Okay. MMA gets it right more or less. Directly engaged rainfall. So this is one of the challenges of improvement of that. Okay. And then how is the El Nino going? It has been pretty much close to zero. It slightly went up then in October. This is not relevant to us. During the monsoon period, it's not going to go very far from zero. So it has no role to play in this year's monsoon. That's why things are easy. We look at IOD, that's a little more complicated. IOD suddenly dipped in August to minus 1.8. So a lot of people say, see, that's what caused the drought. But I don't think so. I think this is a consequence of the Indian monsoon. Okay? Because it's too close to India, it could have the ocean. So it's not going to be something like El Nino or Atlantic, which is far away. This is going to react to your monsoon system. So it's not going to be, you can't separate the two. So I think this is the consequence of our having a weak rainfall in August. It will recover back and it will go to zero. So I don't think it has any value really. Now let's look at how good was the daily forecast for the last 10 days, okay? And I would say we don't look at actual number, it's correctly predicting the increase, okay? So I would say that it got the right decrease, it got the right increase, both are done well. And now let's compare different, this is GFS. Now let's look at ECMWF. That also is more or less getting the trend correctly. Then we have NCUM, that's a National Center. I would say their forecast is this observation, their forecast is slightly going up and down compared to others. Now, we recall last week that all this happening right now is due to MGO. So the MGO based overall forecast is correctly showing how this rainfall anomaly, the overall anomaly in this case, the cloud system is moving starting from 10th August. This would be 13th, this would be 16th, this would be 19th. So currently predicting the northward movement of this rainfall anomaly into India. So this is clearly MGO connected phenomenon. Okay. And if you recall, ECMW forecast for last week was completely below normal all the way to Japan. With our region being over normal. This is 4 to 11, and I'll compare that with observation. It's very close. I cannot reproduce the same color bar, but it's pretty much right. This is correctly predicted and this is correctly predicted. And so I would say that ECMW forecast, which has been there for 2 weeks, has done very well. And what's going to happen now in the coming week, according to ECMW, this system is going to be here for the entire week. And we are going to have a dry spell, which is already starting. And so this is what is going to change the August rainfall, this 1 week of rain. And so I looked at what are the forecasts of Bangalore, okay, just for curiosity. This is predicted from the, in IMD, you have to do all kinds of gymnastics to get the right data. This is from the agricultural section, okay? So it says the next 5 days, rainfall 1, 1, 2, 3. Okay, that's almost no rain. So today's rainfall was 0. That is last yesterday 8:30, today 8:30, there was no rain. So I would say this wasn't there at all. 1 or 2 millimeters is as good as no rain. How about next week, 25th August? This system moves further north. So there's more rain in central India. No, in Indo-Gangetic Plain, we will have a very dry spell, which was forecast by WM even 2 weeks back. So that remains unchanged. And if you go further to the first week of September, which is important, it will be more or less normal. This will be weekly above, weekly below. I would say this week will be normal. Let's see what the result is next week. Okay. Now I want to end on this question about the cloudburst, which always bothers me that our media completely misrepresents. Okay. So I told you there was no cloudburst in Uttarakhand. That event was a glacial lake outburst flood. But unfortunately, even today, after 15 days, they have not identified which lake burst. Now, why is that? Because this terrain is very hard. That particular valley, the Kir Ganga, nobody can go. It's very difficult. There is no path. So these are the glaciers. One of them, glacial lake, one of them can go like that. But this valley is very steep and hard to travel there. So until the cloud clears from Uttarakhand, they can identify which particular lake was formed, or more than lake, the possibility Dr. Kulgan tells me is there are huge ice slabs because these are high latitude region. Entire ice slab will come down. Okay? That is the worst case scenario. That could also happen. And there is a group, I don't know how many of you know, I've been there for a long time, South Asian Network on Dams, Rivers and People. They've been fighting for ordinary people, but I don't think they've succeeded. So they keep reporting, and they think this is where the region where the glacial lake was there, and this is the cave from where the water came and Bhagirathi over here. Okay. So that's their claim, and so I hope in a few weeks before the end of our discussion, we'll know exactly which particular thing did that. because if it's going to be a huge ice slab due to global warming, that's a dangerous situation because you cannot predict it. Lakes you can predict. Almada Kulkarni has done a lot of work identifying lakes all over Himachal Pradesh, where he says access is easier than Uttarakhand, interestingly. And if this is the second event in Uttarakhand, the other one was in the Nandadeva Sanctuary. From there it came. These are very high altitude regions which are thick ice slabs on the slope of the mountain. And if whatever reason it starts melting and the whole thing comes down, that is unpredictable totally. Okay. So this second event has happened in about 4 5 years. So this is a huge cause for concern. Okay. So next week we are not meeting because Wednesday is Ganesh Chaturthi, it's a holiday. So we'll meet week after 3rd September. And the person who will go down is Mahendra, right? Mahendra, okay, yeah. Thank you.
Podcast.